Okay, organic chemistry. So these are going to be the very basics, and it's not really hard at the beginning, right? But I'll tell you what's hard is organic chemistry in college when you've never seen it. That's hard because they're assuming that you are already at point C when you haven't even learned the beginnings. So we're going to go through this slowly, and we're going to build upon it. And by the end of today, you will be able to write out and name organic compounds. Okay? So, first off, organic chemistry is the chemistry of carbon, specifically carbon. Every organic compound contains carbon. And it's the most versatile element. There's over 6 million compounds that contain carbon. So, because there's so many, it needs to be treated a different way. What you've done so far is what we call inorganic. All right, compounds that involve metals, ionic compounds, those kinds of things, that's inorganic chemistry. Organic chemistry has its own set of systems of naming and patterns and reactions. Okay, so we're just going to dip our toe in that today. So first, some general properties. Organic compounds will have low melting and low boiling points. And so if you think of any example that we've ever given you where something melts very easily or is soft or is just not very hard, it's an organic compound. They are soluble in other organic non-polar solvents, not very soluble in water, right, in general. They can be soluble in water, but if they are soluble in water, it means they need something to help it become soluble in water, which we'll get to probably tomorrow. Poor conductivity or no conductivity. Slow reaction rates. We have not yet talked about reaction rates. That's a different unit called kinetics. And low percentage yields. So when we say low percentage yields, you think some of the yields that you've seen in lab were low? You just wait. Right? Organic reactions, yields, some of them can be really low because a lot of these organic reactions are very temperamental. And you need to get conditions so perfect so that you can get a 30% yield. There's lots of variability, there's lots of variation, there's lots of just other things that can happen. So, how do you know if it's a covalent compound? Well, it contains carbon. And we've discussed earlier when we talked about bonding, carbon can form 4 bonds. That can be a combination of single, double, or triple bonds, right? But carbon will form 4 bonds. Usually to hydrogen and oxygen, also to nitrogen, also to halides, so other nonmetals. Hydrogens and halogens will form 1 bond. So when you see that here in the context of what we're talking about, if there's a halogen involved, it's just on a single bond. Oxygen will form 2 bonds, so it'll either be a double or 2 single bonds. Nitrogen will form 3 bonds, so singles, double, triple maybe. Okay, and you've seen this now, and you should understand why this is the case through formal charge. Right? Remember the goal of elements when they bond, or not goal, not the right word. The most stable arrangement is when you see formal charges of 0. And in the case of nitrogen, 3 bonds, oxygen, 2 bonds, and so on. Okay, so different types of formulas. There is what we call the molecular formula, and this is the formula that you are most accustomed to seeing, right? So something like this, C2H5OH. What this tells us is the number of each atom in the compound, but does not give us any information as to what bonds there are. The information about bonds has to be implied, all right? So it's just bare bones information. It's what we use for balanced equations, right? But there's a little bit more we can get. We can write what's called a structural formula. Structural formula tells you the type and number of each atom and bond locations. So when you see a structural formula, I guess you could also call this a Lewis diagram. That would be appropriate to do so. This tells you what's bonded to what. Whereas in the first instance here, it's implied what's bonded to what. Okay? So this gives us more information, but the downside to doing it this way is that's more time consuming. Then there is the condensed structural formula, and this is brand new. A condensed structural formula is a shorthand representation. It omits bond lines, but it still gives you bonding information based on sequence. So these three formulas here, they all represent the same compound, but the difference is that in the structural formula, by first writing CH3, the condensed structural formula is always based on carbon perspective. Based on carbon's perspective. So when we look at this formula and we see CH3, CH2, OH, those H's that follow each carbon are attached to it. So to draw this, there's the C, there's 3 of these H's attached to it. Next up is another C, there's 2 H's attached to it. And then there's the OH. So the bond lines kind of can be filled in after the fact. But the point is, how we write this and how we write this, they kind of look like they provide the same information, but this is faster and more efficient to do than this because you're not taking the time to draw in all those lines. Okay, we're going to be using this a fair amount today. And once we start dealing with more organic reactions, you're going to start seeing this a lot. Okay. So let's talk about the simplest type of organic compound. So we call an alkane. An alkane is also known as a saturated hydrocarbon. What this means is that all carbon-to-carbon bonds are single bonds. And the fact that it's saturated means there's the maximum number of hydrogen atoms bonded. So in other words, wherever there can be a hydrogen bonded, there will be a hydrogen bonded. Okay? Completely flush with hydrogens. Now there's a generic formula to this. CnH2n plus 2. I know it's kind of small there. Right? So whatever the number n is, n represents the number of carbons. And so what this is saying is that for hydrogens, there will always be 2 times the number of carbons plus 2. So whatever the number of carbons is, if n equals 3, this would be C3H8. If n equaled 10, this would be C10H22. Okay, that's the pattern. The reason why you're adding 2 is because you'll be adding a hydrogen to the first and last carbon. Like, because we draw these like a straight line. So if I were to draw this guy, C3H8, 3 carbons in a row, H's wherever they can be bonded, and remember, carbon makes 4 bonds. So if we draw each carbon maxed out with 4 bonds, then H's will go wherever they can be bonded, and that means C3H8. Okay, so alkane, only single bonds between carbons and maximally bonded to hydrogens. So to name these, there's a couple rules of naming these. The first rule, and it probably makes sense to do an example while we're looking at the rules. So let's first look at this guy right here. Okay, to name this, that's actually not right. But actually, well, here, we'll name it anyways. I guess this, what I'm saying is this is not right. Okay. Find the continuous chain, the longest continuous chain of carbon atoms. So when we're looking at this molecule here, we can go left to right. I see 1, 2, 3 carbons. or we can go top to bottom. I see 1, 2, 3 carbons. Either way, the longest chain is 3 carbons long. Okay? And the prefix for 3 is prop. The suffix, because this is all of the carbons have only single bonds, this makes it into the alkane category, the one we just talked about. So the root name of this is propane. You know what? Sorry, I'm going to jump out of order here. This is probably a little too advanced. I'm going to give you a simpler one first before we do this guy. Here, let's just do this. If there are H's everywhere they can be on this molecule here, how would we name this guy? Right, this is hexane. And the formula is C6H12. Okay. The most basic alkanes are straight lines. But it is very common to have what we call branches. So if I were to draw this again, and I'm just going to omit the H's for the sake of simplicity here. All right, so just assume there's H's everywhere there can be. But let's say that I had a branch here. That is a 14. See? It's 14. Okay, if there is a branch, so this is where these rules start to come into play. Find the longest chain, longest continuous chain of carbons. And here it would be 1, 2, 3, 4, 5, 6. Okay, so the parent name of this is also hexane, but this is going to be a longer name because there's more going on. So hexane. Now, find the branch. This is the branch. How many carbons long is the branch? Well, this is the simplest branch there is. There is only 1 carbon. So the prefix for 1 is meth. And the suffix for the branch we use is YL. So this will be what we call methyl hexane. Because the branch is 1 carbon long, that's where the meth comes from. Right? The fact that it's an alkane branch is why the YL suffix is there. Okay, now there's 2 ways you can look at this. If we name this, we have to name the branch based on the numbered carbon it's on. So if I count from left to right, it's 1, 2, 3, 4, 5, 6. Each of those carbons has a number. But if I count from right to left, this is 1, this is 2, this is 3, 4, 5, 6. Because there's 2 directions to count from, we need a pattern to keep us consistent. So what you do is you find whichever sequence puts the branch on the lower numbered carbon. So the left to right sequence is that. And the numbered carbon that we should use is 3. So the name of this compound is 3-methyl hexane. Yeah.
Is the position where it's attached affect its bodies?
Yes. Yeah. Okay. Let's do another one. Just use some space here. Okay. So there's this guy. First step, find the longest contiguous chain. There's 2 ways to count this. You can count it this way, or you can count it straight across. which way gives you the longest number of carbons in a row? Horizontally, how many are there?
6.
What about the yellow path? 1, 2, 3, 4, 5, 6. It's actually the same. So in this case, either way doesn't matter. Okay, so the longest chain is 6, so this is also a hexane. Now there is a branch. Now which one is the branch is up to you. It's based on whichever one is not the longest chain. So we'll make the orange one here. We'll make this the branch. Okay. How many carbons long is the branch? 2. So how do we name that branch? Ethyl, right? Because the prefix for 2 is eth. So what numbered carbon is that ethyl branch on? Now this is where you count either right to left or left to right. Which one puts the ethyl branch on the lower numbered carbon? Right to left, right? So I'm going to call this carbon 1, 2, 3, 4, 5, 6. All right. If we counted the other way, the branch would be on carbon 4. Do you guys see that? So we're going to go with that. So this is 3-ethyl hexane. That's the name. All right. Now, we can have a molecule that has more than one branch. And if it has more than one branch, then there's 2 branches to name as well as number. So, something like this. The longest chain here is how many? It's 4. So what is the name of the parent chain? The prefix for 4 is bute. So this is a butane. Now, the branches. There's 2 branches, and they're actually identical. They're both 1 carbon long. So how do you name a branch that is 1 carbon long? Methyl. But the fact that there's 2 of them here and they are the same means this is a dimethyl. It's 2 branches of the same length, right? They're both 1 carbon long. Okay, so the last thing is to identify what carbon these branches are on. So if I count left to right or right to left, the outcome actually doesn't change. Because if you see, either which way I count, if I count from left to right, the carbons are on carbons 2 and 3. If I count right to left, the carbon branches are still on 2 and 3. So in this case, nothing changes, but you do have to indicate that the branches are on 2 and 3. So the name is 2,3 dimethyl butane. Okay. All right, so back to the original one here. It's provided in the notes. Your longest chain is 3 long. So this is a propane. You've got 2 branches, both the same length. So this also is a dimethyl. Those 2 branches are both on the same carbon. carbon 2. So this will be 2 comma 2. Because you use a number for each branch, since there's 2 branches and they're both on 2, we indicate it as such. How are we doing? Okay. So take a second and name this guy. So, do we have any guesses? Okay, so here let's talk through this. First, what's the parent chain? This is a pentane, okay. Now, you have 2 branches. One of them is 2 carbons long, one of them is 1 carbon long, right? So the 2 carbon is ethyl and the 1 carbon is methyl. Numbering wise, we should go this way. Okay? So when you name this, you go alphabetically in order. So the ethyl comes before methyl, and the ethyl is on carbon 3, so this is going to be 3 ethyl, comma, 2 methyl pentane. Make sense? Okay. All right. I'm going to insert a page here. I just want to do a little bit more practice. I'm not sure you guys are ready for the next section yet. So, let's draw another one. Oh, actually, here, while we're here, where did it go? While we're here, let's get you familiar with condensed structural formulas. So the condensed structural formula, remember, does not show any lines. So the way that this would be shown in a condensed structural formula would be CH3, which is this carbon, okay? CH parentheses CH3, because what that parentheses means is this is a branch. This carbon is this guy. And then CH parentheses CH2 CH3. So this guy, the CH guy, is the 3rd carbon, and he has the branch that is the ethyl. And then CH2 CH3. You see how that works? If there is a branch, you put the branch in parentheses after the carbon that it's attached to. Okay? All right, so let me give you a couple others.
So we're naming these, right?
Name these, yeah. So it's don't ever assume that the longest chain is simply going to be the one that goes left to right. You actually have to physically count and see where the longest chain turns and bends, because it might turn and bend. So for the first one, what is the longest chain? Isn't it 5? The longest chain. Perspective, because organic compounds wiggle and writhe. They turn around, they rotate. So they're not 3D, so you can't assume that it's been drawn with the longest chain shown to you. So if this longest chain is 5 long, this is a pentane. So how do you name the rest? 2 methyl pentane, right? Because we have to go with this being carbon 2. If that's not carbon 2, if we counted it the other way, it would be carbon 4. But you always go with the lowest number carbon available. Okay? What's the longest chain in the second? 6, yeah. So, straight across. Your branches, you have 2 branches and they happen to be the same length. So if this is a hexane, the branch, how do you name a branch of 2? Ethyl, but there's 2 of them, so this is going to be a diethyl, and they are on carbons from left to right, right to left, doesn't matter, the numbers stay the same. It's going to be 3, 4 diethyl hexane. How are we doing? Good? Okay. All right, so this is how you name alkanes, and the principal defining feature of an alkane is what? All single bonds between carbons, which means they are saturated with hydrogens. Okay? All right. Let's talk about the second category. An alkene is when there is one double bond between carbons. Okay, so however many carbons there are, somewhere in there, there is a double bond. And so because there's a double bond, you can't have as many hydrogens bonded. So your formula is CnH2n. Okay, notice how this is different. We are not adding 2 extra hydrogens. This will actually have 2 less hydrogens than an alkane would. Okay, so your H's are just simply double the carbons. So, example. Because carbon can only form 4 total bonds, you have to remember that if there is a double bond, that carbon cannot carry the same number of hydrogens. And this is something that's easily forgotten. Okay, so there's a double bond here, and so we would name this. You're using the same logic as you would an alkane, but you're using a different suffix. Instead of alkane, this is an alkene, which means your suffix is ene. So this would be propene. Now, because there is a double bond, this adds a layer of complexity to when there is a branch. So I'm going to scroll up and use some of the space that we didn't use earlier to go over some more examples. All right, so let's say that this is our compound. And again, I am foregoing hydrogens just for the sake of brevity here. Okay, so this is parent chain of 5. There is a double bond. When the double bond is non-terminal, meaning it's not at the end, because terminal means at the end. When it's non-terminal, you have to indicate with a number what numbered carbon that double bond starts at. So this is propene, but the carbon starts in carbon 2. So this is 2. I'm sorry, pentene. This is 2-pentene. Okay. Now, what if I drew this? How would you name this one? Yes. This is exactly the same as this. The only difference is if we flipped it around 180 degrees. Because the order in which you read your carbons, it doesn't matter if it's literally written left to right. You have to find the longest chain, and your double bond has to be on the lowest numbered carbon, whichever one is available. Yeah, Mattia.
Why aren't the double bonds in the illustrated taken out of the covalent?
Oh, okay. So there's no resonance here because these double bonds are the product of site-specific reactions, meaning when this was formed, there was specifically smaller molecules with what we call functional groups, and those functional groups are fixed in place. And when they combine, if the result is that an oxygen gets pulled off, the double bond that was on that carbon still retains the double bond. It stays there. So there's no resonance because carbon... what's a better way to say this? I guess there's no real central carbon, right? When you have a string of carbons, which one's a central carbon, right? And the principle of resonance is based upon delocalized electrons about the central carbon. This is something called molecular orbital theory, which we didn't cover. Okay, so basically it's going to be a non-issue. All right. So if we have a double bond and we have a branch, do you remember how we said the branch has to be on the lowest numbered carbon possible? but how I just also said a few minutes ago that double bond has to be in the lowest carbon number possible. So now we have a conflict. And so the double bond wins the lower numbered carbon. Okay, so this would be named, well, first let's count out how many we have. We got 1, 2, 3, 4, 5, 6. Okay, so this is going to be a hexene, and double bond is on the second carbon, so this is 2-hexene, which means the branch, which is a methyl, will be on carbon 4. Okay, so if you come to a crossroads and you have to decide to give something a lower number, the double bond takes precedence. Okay, so see if you guys can name this guy. All right, so what do you think? Okay, between that, I think I heard it, yeah. So our longest chain is 7 long. So this is definitely a heptene. Double bond begins at carbon 3, so it's 3-heptene. There's 2 branches, both of the same type, so this is dimethyl. And they are in carbons 2 and 3. So when you're naming this, it's easiest to work backwards. Go with the longest parent name first, identify the branches, and then the number of the branches. Right, and the fact that the carbon begins in carbon, or the double bond begins in carbon 3. Okay, so those are alkenes. The principal defining feature of an alkene is a double bond. Okay. So then, the third category is what we call an alkyne. Y-N-E. An alkyne has a triple bond on a carbon somewhere. Because there's a triple bond, there's even fewer hydrogens, so the formula is CnH2n less 2. Okay, so all of the same naming principles apply here. If there's an alkyne, then then wherever that triple bond is, the carbons involved cannot bond to hydrogens. Because remember, each carbon can only form 4 bonds. So this carbon here has got 3 to the left, 1 to the right. This carbon here has got 1 to the left, 3 to the right. So this guy would be named as what? It's still, you just count, you count them, the longest chain still, and wherever the triple bond begins, that has to be noted.
It's still like ENE or
YNE.
YNE.
pentyne. 2-pentyne. Okay. Good question. Let's go back and let's add structural formulas to these guys, because you'll have to be able to do these with all of them. So back to this guy here, the alkene. To write a structural formula for this, remember condensed structural formulas don't actually have lines, but you go in order based on the carbons. So this would be CH2, CH, CH3. And it's from the lack of hydrogens that multiple bonds are interpreted. So if you ever see a CH in the middle of a carbon chain, all right, that means that that carbon is involved in a multiple bond. Because otherwise it would be CH2 if it was in the middle. Okay. This guy here, 2-pentyne, would be, and we'd write it in reverse, because remember this guy here this is carbon 1, this is 2, 3, 4, 5. So your condensed structural formulas always begin with carbon 1. So it would be CH3, which is this guy, and then it would be C, and then it would be C, and then CH2, and then CH3. Let's go back and do the other ones we did on the previous slide. Okay, so for this one here, this 2,3-dimethyl-3-heptene, we said carbon 1 was 1, 2, 3 here. So, and remember that I am not showing you all of the hydrogens on this. We omitted them for the sake of being faster. But wherever there can be hydrogens bonded, there will be hydrogens bonded. So that means there's really H's on this guy here, right? And all around. Not there. So, this one would be CH3, CH, parentheses, CH3, C, parentheses, CH3, CH, CH2, CH2, CH3. Right, that's 7, right? 1, 2, 3, 4, 5. No, 1, 2, 3, 4, 5, 6, 7. Yep. So branches in parentheses. And then why don't you guys do this guy here? What's the condensed structural formula for 4-methyl-2-hexene? All right, who's got this one? Okay. So we got 6 carbons. 1, 2, 3, 4, 5, 6. The branch is on the 4th. The double bond is on the 2nd. Yep. How we doing? Okay, so there is a system in place for this, right? It just takes practice, but eventually you get it. The most common mistake is people forgetting to follow the bend to find the true longest chain of carbons. Right? Sometimes people just read quickly left to right, but they forget the fact that, like here's one. Like I said, what's the longest chain here? If you looked at this too quickly, you might just say left to right, 4. But it's not really 4. What is it? Right, it's longer than that. Okay. Okay. So that's how you deal with alkynes. So alkanes, alkenes, alkynes. The formula is different. Principal feature, single, double, triple bond. Okay. An aromatic hydrocarbon, benzene. We're just gonna explain what benzene is. We're gonna jump right into the C6H6. This is benzene. And what you see here is this is a cyclo that's enclosed. So the cyclo is used for anything that's enclosed. Okay. So the formula, because it's enclosed and your carbons are touching end to end, if you don't have ends, then you lose 2 hydrogens. So your formula is CnH2n, kind of like an alkene. Okay. So, actually I'm going to skip benzene. We'll talk about that later when we need to. So, for example, this, because it's enclosed and there's 4 carbons, this is what we'd call cyclobutane. Prefix cyclo is for anything that is enclosed in a ring. Bute because there's 4, ane because everything is singly bonded. So what if we had a branch like that? Then this would become methyl cyclobutane. Now we do have to number enclosed carbons in a ring. And because there's nothing to distinguish these carbons other than the branch, we can go ahead and make the branched carbon 1. So the 1 often does not need to be written. It's almost implied if it's not there. Okay? So what about something like this? Yes, this is 2 methyl groups, and you set the number. You decide which carbon is important to get the lower numbered. In this case, the 2 are right next to each other, so we can go ahead and call this guy 1 and this guy 2. It doesn't matter if you went the other way because they both have a methyl on it. So this would be, work backwards. So this is a cyclopentane. It's a dimethyl cyclopentane, and it's 1, 2. Okay.
The cycloalkanes, how do they differ from others so you can see, like their properties?
So if they're enclosed in a ring, then they have a more rigid structure than a straight up regular alkane, where think of a regular alkane as like a spaghetti noodle, right? So if it's more rigid like this, then opportunities for reactions decrease, right? As well as surface area. So things like London dispersion forces will be slightly less effective here than they would be in something that was more just straight. Okay, and that's where we're going to call it